Hello students, welcome to the class of Basic Electrical Engineering followed by the code EE201. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Today, this is our second class of Basic Electrical Engineering, and during this class, we will discuss on the concept of phasor diagram. During this video lecture, we will discuss on the introduction to the phasor diagram, its basic concepts, the phasor diagram of a sinusoidal waveform, phase difference of a sinusoidal waveform, the concept of leading and lagging. So we have already pointed out that it is assumed that alternating voltage and currents flow in a sine law, and generators are designed to give EMFs having the sine waveform. Now this assumption makes the calculation simple, and the method of representing alternating quantities by waveform or by the equation gives the instantaneous value is quite cumbersome. For the solution of AC problems, it is advantageous to represent a sinusoidal quantity that may be voltage or current by a line of definite length rotating in counterclockwise direction with the same angular velocity at which the sinusoidal quantity has. And this rotating line is called the phasor. And phasor diagrams are the graphical way of representing the magnitude and the directional relationship between two or more alternating quantities. So in standard convention, the phasor is rotated in counterclockwise direction, and a convention that is the harmony with the general use of the polar coordinates. And sinusoidal quantities are scalar quantities which are varying periodically with the time according to the definition of vector quantities. They are not the true vectors. Now voltage is simply energy or work per coulomb and cannot be classified as a vector. Current is also not a vector quantity because it has the flow of electrons through a wire, but keeping in mind that any sinusoidal quantity at a given frequency is completely specified by its amplitude and phase angle, its similarity to a vector. Now for the difference of term phasor has been considered instead of the term vector for representing graphically the magnitude and phase of a sinusoidal voltage or current. So we have to keep in mind two things during the drawing of the phasor. So first one is the angle will vary in the counterclockwise rotation direction. That means the phasor is rotated into anti-clockwise direction. And all the phasors are drawn reference to the horizontal zero axis. And phasor diagrams can be drawn to represent more than two sinusoids. They can be either voltage or current or some other alternating quantity, but the frequency of all of them must be same. And always the phasors are drawn in an anti-clockwise direction. So these are some basic concepts. As the phasor diagram can be drawn to represent at any instant of time, therefore the reference phasor of an alternating quantity is always drawn along the positive axis, And vectors, phasors or phasor diagrams only applicable for the sinusoidal AC alternating quantities. All the phasors has been drawn from the reference, that is the horizontal zero axis, and phasor diagrams can be drawn to represent more than two sinusoids. They can be either voltage or current or some other alternating quantity, but the frequency of all of them must be same. All the phasors are drawn rotating in the anti-clockwise direction. All the phasors ahead of the reference phasor are said to be leading, while all the phasors behind the reference phasors are said to be lagging. Now, sinusoids of different frequencies cannot be represented on the same phasor due to the different speed of the vectors. At any instant of time, the phase angle between them will be different, and the length of phasor represents the RMS value of the sinusoidal quantity rather than its maximum value. Two or more vectors can be added or subtracted together and become a single vector, which is known as the resultant vector. Now, the sinusoidal wave can be represented as A max sine omega t, which represents sinusoid in time domain form, but when represented mathematically, it is very difficult to visualize the angular or the phasor difference between two or more sinusoidal waveforms. Now, we can overcome this problem by representing the sinusoids graphically within the spatial or phasor domain formed by phasor diagrams, and this is achieved by rotating vector method. Now consider the phasor diagram of a sinusoidal wave. So if we consider the center as O, then this OA, or it is a phasor, represents to scale the maximum value of an alternating quantity. Now this OA represents the A max and rotating in the counterclockwise direction at an angular velocity omega radian per second about the point O. Now the arrowhead is put at the outer end of the phasor. Please indicate which end is assumed to move and partly indicate the precise length of the phasor when two or more phasors happen to coincide. Now the phasor OA, it has rotated through an angle theta and it will become equal to omega into t. From the position occupied, then the EMF was passing through its zero value, and the projection of OA on x-axis and y-axis. So in y-axis, it is, we can write here, this is equal to E, which is the value of the EMF at the given instant. Now the projection of OA on the vertical axis represents to the scale of instantaneous value of EMF. Now it can be seen that phasor OA is rotating in counterclockwise direction and it will represent a sinusoidal quantity if its length is equal to the peak or maximum value of sinusoidal voltage or current to a suitable scale. It is in horizontal position at the instant the alternating quantity is 0 and increasing, and its angular velocity is such that it completes one revolution in the same time as taken by the alternating quantity to complete the one cycle. So after complete rotation of this phasor, there is one cycle of sinusoidal has been generated. So next is the concept of phase difference of a sinusoidal waveform. So as there is definite relation between the maximum value and RMS value, the length of phasor can be taken equal to the RMS value if required. But projection of rotating phasor on the vertical axis will not give the instantaneous value of that alternating quantity. Now the phasor diagram drawn in RMS value of the alternating quantities helps in understanding the behavior of the AC machine under different loading condition. Now the phase of an alternating current represents the fraction of the time period of the alternating current that has elapsed since the current last passed through the zero position of the reference. So the phase angle of any quantity means the angle the phasor representing the quantity mixed with the reference line. For an example, if we consider here the voltage is Vmax sine omega t, whereas the current has been generated before this zero position. So it can be represented by I is equal to I max sine omega t plus minus phi. So the phase difference means when two alternating quantities, it may be two voltage, two current, or one voltage or one current, are considered simultaneously, the frequency being the same, they may not pass through a particular point at the same instant. One may pass through its maximum value at the instant when the other passes through the value other than its maximum value. Now these quantities are said to have a phase difference, and phase difference is always given either in degree or it can be expressed in radians. Now the phase difference is measured by the angular distance between the points where two curves cross the base or reference line in the same direction. The quantity ahead in phase is said to lead and the other quantity, while the second quantity is said to lag behind the first one. So in this figure we can see that the voltage represented by this phasor is the leading position rather than the current. So, or we can say the current I is lagging behind the voltage by the angle phi, and here the phi is equal to 30 degree. So here we can say the concept of leading and lagging. The phasor diagram is drawn corresponding to 0 or t equal to 0 on the horizontal axis, and here we have taken V is in the reference axis, so it has been expressed as V max sine omega t. Now the current is lagging, so it is lagging behind by 30 degrees. So it has been written as I max sine omega t minus phi, where phi is the 30 degree. Similar way, we can express the current in the reference phase, and the voltage is leading by this current by an angle phi. So one phasor is designated as the reference phasor, and all other phasors will be either leading or lagging with respect to this reference. Next is the phasor diagram. So there are some conventions for drawing the phasor diagrams. So as already we have discussed, the alternating quantities are represented by straight lines having the definite direction and length, and such lines are called the phasors, and the diagrams in which the phasor represents the currents or voltages and their phase difference are known as the phasor diagram. Now the phasor diagram can be drawn to represent either its maximum or the effective value of voltage or current, but since the effective values are much more important, phasor diagrams are mostly drawn to represent the effective values. Now to achieve the consistent and accurate result, it is essential to follow some conventions, and these conventions are that the counterclockwise direction of rotation of phasor is usually taken as positive direction of rotation. That is, if a phasor rotated in counterclockwise direction from a given phasor, it's said to be lead the given phasor, while the phasor rotated in the clockwise direction, it is said to the lagging phasor. For the series circuit in which current is common to all parts of the circuit, the current phasor is usually taken as the reference phasor. For the other phasors, the same diagram and drawn on the horizontal line. In parallel circuits, voltage is common to all branches of the circuit, so the voltage phasor is usually taken as the reference phasor and drawn on the horizontal axis, and the remaining phasors are referred to the common voltage phasor. And it is not necessary that the current and voltage phasors are drawn to the same scale. In fact, it is often desirable to draw the current phasor to a larger scale than the voltage phasor when the values of the current being represented are small. And if several voltage phasors are to be used in the same phasor diagram, they should be drawn at the same scale. Similarly, all current phasors in the same diagram should be drawn to the same scale. So now after this conventional method, now we are going to learn how to add two phasor. or the phasor addition. So if we say that two voltages of 50 volt and 25 volts are respectively together in phase, and they will form one voltage of 75 volt. But if they are not in phase, then the phase angle between them needs to be taken account. So they are added together using the phasor diagrams to determine the resultant phasor or the vector sum by the parallelogram law. So here we can consider that V1 having a peak voltage of the 20 volt and V2 having the peak value voltage equal to 30 volts, and V1 leads the V2 by 60 degree. Now the total voltage Vt of these two voltages can be found by firstly drawing a phasor diagram represent the two vectors and then constructing a parallelogram in which two of the sides of voltage are V1 and V2. So here we can add the graphically by plotting the curves in the same system coordinates, and it is a simpler and more direct method using the phasor addition. Now how to calculate this? So the horizontal component is 30 cos 30 degree 0 degree, so it becomes 30 volts, and vertical component is 30 sin 0 degree, so it gives us 0 volt. Now for the rectangular expression, V2 becomes 30 plus J0 because the imaginary part is the vertical component and that is 0. And V1 of 20 volts leads the voltage and V2 by 60 degree. So both has horizontal and vertical components, and horizontal components becomes 20 cos 60 degree, whereas the vertical component is 20 sin 60 degree. It gives us 10 volts and vertical component of 17.32 volts. So the total voltage V1 expressed as 10 plus 17.32 J. So the resultant voltage can be found out by adding together the horizontal and vertical components, and as per the Pythagoras theorem, it will be root over of real part square plus imaginary part square. So the real part is 30 plus 10, that is equal to 40 square, and the imaginary part is 0 plus 17.32, that is the 17.32 square. So overall Vt becomes 43.6 volt. So in this way you can add two or more phasors. So two or more alternating quantities may be added in the same way as the voltages are added here, and by constructing the parallelograms or closed polygons and either measuring or calculating the length of the diagonals or closing sides and the magnitude of the phase angle. So this method is more convenient when two phasors are need to be added. Next is the resultant value of V2. So we have found out that the horizontal component is 40 and the vertical component is 17.32, and as per the Pythagoras law, Vt is equal to root over of V1 square plus V2 square, which gives us the phasor sum, and that value is 43.32. Next is the phasor subtraction. So during this phasor subtraction we can use the same method just in the opposite way, because if we add two numbers a plus b, that and if we subtract a minus b, that is same as if we add the minus b vector with the a vector. So in here we can draw the opposite, that means 180 degree difference, that means the plus b and minus b has 180 degree difference, and then we can add both a and minus b to get the total resultant vector. So here we can write a is equal to x plus jy, and b has the horizontal and vertical component w plus jz, and a minus b represents x minus w plus j of y minus z, just like the same way. So hope after this video lecture you have a clear idea about today's topic. Now we will go through some question answer session in context of this video lecture, and you are requested to go through it gradually and solve it by your own. All the answers and the explanations are attached at the end of each question.